Hello everyone, welcome back to machine learning sessions. In this session, we'll discuss about KBANN algorithm. So this algorithm is to initialize the hypothesis using the prior knowledge that is given. So this KBANN algorithm uses prior knowledge to initialize the hypothesis to perfectly fit the domain theory, and also it will intuitively refine this initial hypothesis as many times as needed to fit the training data. So let's get into the algorithm. So before to that, so let us see what are the initial assumptions. Initially, a set of training examples will be given to you and a domain theory consisting of non-recursive and propositional horn clauses will be given to you. So I hope all of you know the meaning of a non-recursive horn clause. So what is meant by recursion? Suppose if both, here if you see father of x and y and daughter of y gives rise to granddaughter of x comma y. So in this case, don't worry about the propositions, only focus on the variables that we are using. So here if you see x and y are there on the left hand side, same things are there on the right hand side also. So that means this will give rise to recursion. So I should not have these kind of things. Okay, so then I should have a clause which is in the form of p of x gives rise to q of y. Let me take a pen. P of x gives rise to q of y. The same literal or the variable should not be there both on the left hand as well as on the right hand side. So then coming to the horn clause, at most you will have one positive literal, rest all will be negated ones, right? So now given this kind of clauses, so you have to determine an ANN which will fit the training examples biased by the domaining theory. Okay, so whatever ANN you are designing, it is purely based on the domain theory that is given and based on the training examples. So there are two stages in the KBANN algorithm. So the first one is creating an artificial neural network which perfectly fits the domain theory. And the second one is use the back propagation algorithm to refine this initial network. Okay, so first initially some training examples are given. Okay, so to classify all the training examples as positive, suppose if the domain theory is not enough, okay, so it is not, that means the number of clauses that are given in that are not enough. So then what we did in the earlier example, so there we try to refine the domain theory. So we try to add some more clauses into the domain theory, right? So that can be done with the help of back propagation algorithm. So you can add few and again back propagate and then see whether your ANN is able to classify these training examples with the help of the domain theory or not. So this refinement can be done as many times as you want. So in the let us come to the KBANN algorithm. Okay, so in the KBANN algorithm, so two arguments will be taken. So the first one is the domain theory, second one is set of training examples. Okay, so these training examples are in the form of input-output pairs. So based on this, the first step. Okay, so here if you observe 1, 2, 3 is the first step, which is the analytical step. So the second step, the fourth step is under the inductive step, which is refining the initial network that is created with the help of these first three steps. Okay. So if you see the first three steps, first step, what is it? For each instance attribute, create a network input. So now if you have an attribute, okay, so then you should take that attribute as an input. Now, for each horn clause in the domain theory, create a network unit. So how to create a network unit is connect the inputs of this unit to the attributes tested by the clause antecedents. So what are antecedents? Suppose if you have a clause in the form of A implies B. So this left hand side part we call as antecedent. This is the consequent. I hope all of you know this. Okay, so only this left hand side parts we are taking. So this we are giving as an input. So now we will check whether this is a positive one or a negative one, negated or non-negative. Is it A or negated is negation A? So in which form it is? Okay. So if it is a non-negated one, so that is if it is in the form of A, so then we'll take the weight as positive. If it is a negated one, we will take the weight as a negative one. So then we should have the initial threshold weight also, right? W naught. So this W naught is taken based on this formula minus of N minus 0.5 into W. So here N is the number of non-negated antecedents of the horn clause. Okay. So now the third step, add additional connections among the network units, connecting each network unit at depth I from the input layer to all network units at depth I plus 1 and assign random non-zero weights to these additional connections. So here we are assuming a back propagation network. That means you will be having the hidden layers as well, right? So now, so from input layer I to hidden layer, you will be connecting. Again, from that hidden layer, you can connect to the next hidden layer, and finally you will be connecting to the output layer. Okay, so that's what input layer, your I is the input layer, I plus 1 is your hidden layer. Okay, so at the hidden layer, assign some random non-zero weights to these additional concepts. So here, suppose if the domain theory is not classifying all the examples as positive, or if the number of predicates or the number of clauses given are not enough, so then what you can do is you can add some more. Okay, so to those some more, what should be the weight that you can assume is some random weights you can assign based on your choice. You can assign some random choice. Now when all these weights are perfectly set, then your ANN creation will be done. Okay, so initially it won't be done, right? So you have to modify it number of times. So only we have the refinement step. So okay, so to refine, what we do is we will be applying the back propagation algorithm to adjust these initial weights. So let me show you how this back propagation, try to recollect the back propagation concept. So in the back propagation, what we'll have, we'll have initial set of input layers. So these are the input layers. So these are given to the first set of hidden layers. So this is the first hidden layer. So if you want to have, you can have more number of hidden layers as well. For simplicity, here I have taken only one hidden layer. So now the output that is generated at A and output that is generated at B. So both are given to the output layer. Okay. And here, in order to decide this output, so here whenever X1, X2, X3 are connected to this A, so here output has to be generated. Okay, so here logical and implementation using the sigmoid function only will be done. Okay, so this also we have done in the second unit. If you have not referred to that, please refer to that topic. If you want, I will provide the link in the iCard. You please just refer to that. Okay, so logical AND operation will perform at the hidden layers, and the result again we will be giving to the Y. At Y also a logical AND with the help of sigmoid will be taken. So here the first 1 to 3 steps are the first stage. Step 4 is the second stage. So now, so you can see this is the domain theory that is given. Okay, so as per the domain theory, so what is given? A cup is given. So what are the attributes of this cup should be is a cup should be a stable, and it should be liftable, and it should be an open vessel. So now the definition of these are also given in the further clauses. So what is meant by stable is if the bottom is flat, and then what is meant by liftable is it should be graspable and it should be light. What is meant by graspable is it should have the handle. So then what is meant by open vessel is it has concavity, and concavity should point up. Okay, so concave means it should be in this form, and this concavity should be on the upper side. Okay, and it should also have a handle, and the bottom should be a flat one, and it should be a liftable object. So these are the characteristics that are given. So these characteristics are taken as the attributes. Okay, so now if you see, all these left hand sides are the antecedents: stable, liftable, graspable, open vessel. So these are our antecedents. Okay, so now in order to classify this correctly, so what are the clauses that should be satisfied? So let us number this as 1, 2, 3 and 4. So all these 4 should be satisfied. Okay, so this liftable itself is containing graspable as well as light. Okay, so graspable is defined in one more clause. So we need all these 4 in order to say that particular object is a cup. And here some training examples are given. So if you see the first one, so you can see the left hand side, bottom is flat, concavity is a concavity points up. Sorry, here the equation is taken as A implies B. So these are the antecedents. Always the left hand side. Actually, I'm used to this sort of notation. So on this case, A is the antecedent, but here the notation is given like this. So these are the antecedents. So here you can see bottom is flat, concavity points up, expensive. So here you can see some more added things. Expensive, fragile, handle on top, handle on side. So these are not there in the domain theory that is provided. So some examples are there. So in order to support these, we have to add some more clauses in the domain theory if it is not classifying all these examples as positive. As concavity is there, as handle is there, then light is there, then the property made of ceramics, made of paper and made of uh, styrofoam. So all this is not there. Okay, so these are the extra clauses. So that is what the step 2 is defining. So let's get back to the algorithm and let me show. So here, this third one, add additional connections among network unit. Okay, so why you need to connect these extra connections is in order to add these. Okay, so to add this again, we need to refine. After adding, we need to refine. So now, if you see, so some cups are given, some examples are cups, some are non-cups. Okay, so based on what they are defined as non-cups, based on what they are defined as cups. Okay, so just now we have seen that. Suppose if it is satisfying 1, 2, 3, 4. So the first one, this example is satisfying all 1, 2, 3, 4. So 1 can be taken as a positive one, 2 also can be taken as positive. If you take 3, okay, so it is not having 2 and 4. So it is not justifying 2 and 4. So this is taken as a negative example. Similarly, here 3 and 4 are not there. So this also will be taken as a negative one. So like that. So which is positive, which is negative, that has to be considered. Now, so let us see how to construct the network from this cup domain theory. Okay, so the network is created by creating a sigmoid threshold unit for each horn clause in the domain theory. Okay, so where is the horn clause actually? Do we have any horn clauses? Actually, all are horn clauses only. So how we can say, actually your domain theory is in the form of P implies Q, right? P implies Q. So that means P implies Q is P or negation Q, right? P or negation Q. So we can say all are horn clauses only. So we can construct a network using these clauses. And the sigmoid unit, so as all of you know, the sigmoid output will be, if output is greater than 0.5, it is taken as true, that means 1. If the value is less than 0.5, it is taken as false, whose output value is 0. Now, the output of each unit, so the hidden unit, okay, will be greater than 0.5, where the corresponding horn clauses are applicable. If they are not applicable, anyhow, their value will be 0. As a result, you will be having your output also as 0. So now for each antecedent to the horn clause, an input is created to the corresponding sigmoid unit. So all the P's will act as an input. Now the weights of the sigmoid unit are then set so that it computes the logical end of the inputs. So these weights are again assumed. Only W naught can be computed. The other weights you can simply assume randomly. And in particular, for each input correspond. So this is already mentioned in the algorithm as well. If the input is a non-negated one, so then we'll take the weight as positive. If it is a negated one, the weight will be taken as minus. So now the threshold value is computed using this formula. And now when the input values are 1 or 0, so x1 is 1 or x1 is 0. So then their weighted sum. So how do we compute sigma Wixi? We will be computing, right? The weighted summation is this one. So to this we are adding W naught as well. Okay. So this will be positive if and only if all the clauses of the antecedents are satisfied. If it is satisfied, then we will take it as 1. Otherwise, we will take it as 0. So now, if you see here, so you can see some solid lines and some very light lines. Okay. So this is the first step. So under this first step, an object can be called as a cup if it is stable, liftable, and it is an open vessel. So the inputs to this hidden layer, okay, the inputs to this hidden layer are from this particular input. So here you can see here also we have one more input layer whose output is given to the graspable, has handle, has a hidden layer. Okay. So let it be expensive, bottom is flat, made of ceramic. So all these are the extra attributes which are added based on this. This graspable has got an input. Okay. So the output of this hidden layer is given as input to this graspable one. Okay. So now, so considering all this, the output at stable is considered, output at liftable is considered, and output at open vessel is also considered. So now let us assume that for these solid lines only we have the output as 1 and rest all are taken as 0, which are very negligible values. So then in that case, let us take 1, 2, 3, 4, only 5 positive ones let us take. So then the W naught will be computed as minus of n minus 0.5 into W. So usually this W is taken as 4.0. So as per the computation of the KBANN algorithm. So this value has given positive value in most of the cases. So this W value is assumed as 4.0. So what is your W naught? Minus of 5 minus 0.5 multiplied with 4.0 or 0.4. 1 second. Let us check the value. So it is 4.0. Yeah, fine. So now this will give rise to 5 minus 0.5 is 4.5 multiplied with 4. So this will give us a negative value. Okay. So you are getting a large negative value. So which will be multiplied with a positive value of 1. So all the ones are. So here we are taking all the ones, right? So if you compute the output, so here you can see only one solid line is there. So this we will consider as 1. So rest all we will take as zeros. So first let us compute W naught at this particular node. Only one we will consider. So I started with all. So means to compute the output here. But for that I need output at this first level, at the first hidden layer. So let us compute this W naught first. So it is given as minus of n minus 0.5 multiplied with W. So this W value is taken as 4.0. That is a value that is given by the KBANN algorithm. If you want, you can take some other value as well. But that might take more number of passes in order to stabilize your network using back propagation. Okay, so here, so n value. So here, how many positive non-negated ones are there? Only one solid line. So that means only this is there. So in this particular case, let me take it as 1 minus 0.5, which will give me 0.5 multiplied with 4.0. So that gives me a value of minus 0. So I'll be getting a value of 20. Yeah, so it is 0.20. So now I have to compute the weighted summation, W naught plus the weighted summation. Okay, so like this some value I might be getting, W naught I got. So now W1, let me assume the weight here. So this is W11, the weight at this particular one from here to here. Okay, so these are W11s. This is W12. So I hope you know all this notation. So this is W21. And from here to here, whatever weight goes, that is W22. So from here to here, the weight that goes is W23. And the input also, let us take it as Y1, otherwise Y11 you can take Y12, and this we can take it as Y13. So W0 should be multiplied with this particular value. So this is the weighted summation. Okay, so at the last node, so based on this W0 and based on these weights, the summation of all the weights if you take, so you will be getting some output at this particular node that we are considering as Y11. So now if you see the output at this particular node, it is nothing but summation of all these output values, right? So using these weights, when you perform a weighted summation, so you will be getting your output, which is nothing but W21 into, if you want, you can assume a bias at this intermediate stage as well. So to make the process simple, I'm not assuming the bias here. W22 Y12 plus W23 Y13. Okay, so based on this, when you multiply all these values, say suppose here I am getting a value of 0.5 and I multiply this. Here I got some negative value, let us assume minus 0.4. So here let us assume that I am getting a value of 0.8. Okay, so when you sum up all these things, 0.8 plus 0.5, which gives me 1.3 minus 0.4. So overall it is giving me a value which is greater than 0.5. So I can say these examples are perfectly classifying this as a positive one. So my ANN is fine with these examples. Okay, suppose if they are not giving me our output which is greater than 0.5. So in that case, what I have to do, I have to back propagate and adjust these weights. Okay, so whatever weights I have assumed for these W21, W22, W23, first this should be modified and we should be back propagated to the previous unit. So there also weights should be modified. So that means I have to finalize what should be the weights of all the first hidden layer and what should be the weights of all the second hidden layer. And here in this example, if you see, the output classifications are given which are satisfying our domain theory. So here dark lines are indicating the connections with weight W and correspond to the antecedents of the clauses, whereas these light lines are indicating the connections with weights which are approximately equal to 0. So only for the dark line, only one weight I have considered. Okay, so like that you can compute W0 and to that you can add the weight of that multiplied by the input value. Okay, so if this input, suppose if the bottom is flat, see, in this solid line, bottom is flat means your input should be taken as 1 because this is justifiable. It is acceptable by our domain theory. So it will be taken as 1. If you take expensive, it is not there in our domain theory. So the input for that will be taken as 0. Okay, so in order to keep it calm and in order to not to consider that particular input, we'll make the inputs of that and weights of that to 0. So other solid lines only we are considering. Okay, so now let us come to the second step. So in the second step here, if you see, so there are a lot more variations. You can see a solid line that is a large positive weight, and you can see some dotted lines as well. Okay, the dotted lines that too very solid. So they are taken as large negative weights, and then we have very light lines also. So okay, so that indicates negligible weights. Okay, so all these are negligible weights almost equal to 0. So here you can see these are all these solid lines are large positive ones and this dotted line is large negative one. And now again, so we'll see whether this example will classify positively or not. Otherwise, we have to use the back propagation and using that we will modify the network weights. So now if you see what is added newly other than if you see the previous example, so in this we have taken only bottom is flat, graspable, light, has concavity, concavity points up. So other than this, what are added up here? So here you can see made of styrofoam is added and handle on top. That though it is a large negative weight, so that is also giving us a positive output value. So we are considering that as well. Okay, so this is done through number of passes went through the back propagation algorithm. Okay, so this is all about the KBANN algorithm. Hope you followed. If you have any queries, please let me know in the comment section. If you like the content, do like, share and subscribe. I want to thank all my subscribers who are giving me a lot of views and with a nice watch time, but I do need subscribers. So please do subscribe. Thank you.